pop. Throw in 110.
Do you have a potentiometer?
What's that?
Potentiometer?
I do, George.
You're so excited about it.
George, thank you. All right.
Set this on the table.
Actually, so first I'll just show you what happens.
Wait.
I need to let the whole time.
I'm going to videotape it.
Okay.
Yeah, power sources.
You can measure the current as you do that too.
So, those of you that are watching, this is just an LED. I'll turn this off first. Plugged in, and I'm about to apply 5 volts to an LED that's only expecting 2.
Damn.
Wait, those of you, it's kind of strong.
No smoke.
No smoke.
Make it blink again.
Oh.
Let's see. Let's turn it back on. No. So this LED is officially dead, and you can't really tell.
Right. I know I put it.
Do we have a microscope yet?
What's that?
Do we have our microscope yet?
I don't know.
Oh, I forgot to bring it. I get what I was going to bring.
No, I will not do that, Sean. Alright, so that's dead. George asked if I had a potentiometer, which is a variable resistor. Right, so this, I believe, is a 100K. So at one end, it provides 0 resistance whatsoever, and at the other end, it provides 100,000 ohms. And yes, magic. I had LEDs, which
I have a 10K here that's got leads on it if you want.
10K with leads, George.
Where is it going?
George, you want to stand up here instead?
Yellow goes to...
Alright, here, never mind. I've got a 10K and I have extra leads.
Okay.
Wait, does that power supply do 12 volts?
Yes, it does.
We should do with 12 volts.
No.
No, let's stick with 5 volts.
We've already proven we can pop it. You don't want to melt it.
It'll just pop fast. Well, it won't melt the breadboard.
Make sure you're starting at the 100K end, Joe.
What's that?
Make sure you're starting at the 100K end.
Yes.
Yeah.
Can you hook up the multimeter across the resistor to see what impedance it blows the diode at?
Sure.
Cool.
Is the voltage or
You mean the current?
No, I want to see what resistance value the diode then blows up, and then we can calculate what voltage it was at.
You'd have to pull it out
What the current was.
The current. Yeah. The diode's always at the same voltage.
Right, because again, it's going to short it. Right. Well, we can just disconnect it once it pops. Yeah. And then measure it.
Right.
You can also butterfly.
Alright, stuff
The meter in series measuring currents.
Yeah.
Right.
And it'll measure the whole circuit. And show you that real time.
So, that's
Yeah. I just want to search here.
Do we have a traditional overhead for that?
traditional overhead.
Probably, if we do, it's stepped away somewhere.
You know what you could do?
Possibly.
Right.
That'd be perfect for these types of things. Yeah.
So,
hard to do.
sit down for this.
Start down with the...
So, for those of you that can see, that light is on. It's on very dim. Does this help?
Yes.
Alright, so I have this set to the highest resistance possible. And as I slowly turn it, notice it's slowly getting brighter. Alright, so now you should notice a significant increase from where it was to begin with. Now it gets really bright. There. And now it's dying, and it's dead.
Okay, what resistance was it at?
Right, so now, what Mike is asking is, what was the resistance? And always turn off circuits before you touch the wires.
Pro tip.
Don't do as I do as I say.
But George
right?
said we were supposed to.
No, that's the paper clip in the outlet. Right, so now if I...
Tongue.
Now, everyone remembers our nominal resistance for this circuit was 150 ohms, right? Have we
Yes.
calculated? Okay,
Right.
what did it blow up at?
Alright. It blew up at 93 ohms. Probably a little bit higher than 93 because of my reaction time. So I was spinning it. As soon as I noticed it get really bright and flutter down, I stopped spinning, but it was probably a little bit higher.
So the moral of the story is don't be Tim Allen. Don't try and reduce your resistance in order to increase your power.
Right. So for LEDs, there's an interesting... So I said there were more things on that the specification sheet than just the continuous current, right? So that's what we've been playing around with. The continuous current is 20 milliamps, but it can have, as you saw, it can get really bright, but if it sustains that, it burns out. So there's also known as a peak current, which can be upwards of 50 milliamps, right, or higher. And if you do that and just pulse it very short time, and all those numbers are on the sheet as well, right? You can pulse it, let it get really bright, wait, and then pulse it again, which is where the microcontroller can come in, right? Because it can do that switching very fast. Then you can get an LED that looks a lot brighter than it does at its maximum continuous forward current by pulsing it. So that's one way to cheat to get a little bit more brightness out of the LEDs, is to not run them at a peak current, but for only a short amount of time. Yes.
Do the LEDs in any circumstance put out any measurable heat?
Any measurable heat?
On an LED.
Yes, LEDs can. But generally, you'll only get that out of LEDs that are really high power. So the LEDs that show up in car headlamps or the really bright flashlights, those are upwards of 1 watt as far as the power consumed, and they actually require a heat sink.
How does the watt relate to the voltage and the resistance?
Okay, so now we're back at the question of power.